Hi, I'm Julia, and today's topic is a quick predictions on small data with tabular foundation model. Let's start with reading an abstract. Can we all read this abstract? For me, first of all, there is no explicit acceptance, but still there is some attractive point that such as outcomes of the business where we can do many things. Do you have any comments or other thoughts?
The sentence was not like although deep learning has revolutionized. It looks like a gap sentence at first, but the comma is kind of weird. It's like, oh, there is something, but you're just using that. They're not really describing a gap. Sentence looks weird.
Yes, right. You pretend to be your gap, but it is actually not a gap.
Why is that not the gap sentence?
So, if it wanting to be a gap sentence, then it should explicitly state the problem of the previous persons, not just for the money, or it but also for creating this interface. Because it is not actually saying with gradient this interface, so maybe because they are developing new models, so we can just pointing out some problems of the gradient usage interface, so that it can be.
I see what you're saying. Yeah, I guess, what they're saying is deep learning's been good for everything else. Why not here? Because gradient boosted decision trees are dominating here. Let's change that. Yeah. You're right. They didn't actually say that there's a problem with these methods. It's like, here's the flavor of the month. Everybody likes these. Let's apply it over here. Maybe that's not a very good reason.
You don't like this abstract?
Oh, well, it can be improved. They can improve their abstract, but I cannot. I think I'm not qualified to judge their abstract because it is largely nature.
This the target of this research is growing. I think its impact is high. we are targeting.
Oh. So let's move on to the introduction. So for the not only for our lab, there's many data set, real world data sets, and if you once get a data set from the experimentalists or doctors, then most of the data set will is in the form of this kind of data. So we have many samples, multiple samples for the rows, and we have many features in the columns like this. And not only for this kind of tabular data, even though we got a time series data, it can be also represented as a table like this. So for the each time, we have a corresponding value for that column like this. So I wanted to say that most of the real data sets, they are already in tabular form, or they can be represented in a tabular form. And if we got this tabular data, and if we want to perform some prediction using this tabular data, then, for example, if we have some insomnia data and age, BMI, sex for each individual, then we will use like age, BMI, and sex for to predict insomnia. Then in this kind of problem, you're usually split the train and test, and by using this feature for training set and the outcome for training set, we are training the model. So actually we are training the model which uses age, BMI, sex information to predict the insomnia. And we are evaluating the performance of this data by using the remaining testing set. So we are plugging this testing set to the model, and we are making a prediction, and we are comparing this prediction with the real data set. So basically, if we have the insomnia data set, then we are making the model for insomnia prediction, and if we have a model for the if we have a like depressive disorder data set, then we are making a prediction model for the depression. But this table structure is maintained. I mean, they are basically in the same structure, but we are making a different model for each data set. So rather than making a like different models for the each data set which have a similar structure, can we make a like universal model which is applicable for the all this kind of table structure data set? So to address this inconvenience, that the authors made TAP-PFN, the new model. And TAP-PFN, what TAP-PFN do is, if we have like arbitrary table data like this, then if we label the training set and test set, then this feature of training set and the outcome of training set and this feature of testing set, it becomes the like whole this whole information becomes the input for the TAP-PFN. Then this TAP-PFN will predict the remaining this Y test variable. So to train this like TAP-PFN, if we want to like predict the Y test with this whole information, then we have to learn some key structure of the key causal structure from X train to Y train, and apply it to the this X test so that we can make a prediction for the Y test. And if you see this kind of structure, then it is somewhat similar with the large language model. So if you think this X train as like our question for the ChatGPT. And if you think this Y train as a the response of the ChatGPT, then what ChatGPT do is based on the previous conversations, they are reading a context and they will make a new response for our new questions. So it is basically have a similar structure with large language model. And this large language model is trained on the many conversation data sets, language conversations. And this, but for this TAP-PFN, we have to train this TAP-PFN with many table data. So training the TAP-PFN is starting from the making of many tables. And to make the table which will be used for the TAP-PFN, we were doing following things. We first sample the data size of the table, such as we are sampling the number of features and number of samples. Let's say we have 5 features and 10,000 samples. Then we have a table like this. And next, and for next, we are again sampling the causal relationship between features. So we can make the causal structure like this. This 1 causes 2, and 2 causes 3, and so on. Or we can make more complex structure, such as 1 and 2 affects the 4, and 1 and 2 impacts 3, and this 3 and 4 impacts the 6. And we, even though I just I draw 2 structures, we can make really many causal structures. And for each causal structure, starting from this, the beginning node, for beginning node, we are sampling the data from some uniform distribution. So we have a random number for the feature 1, like this. And for feature 2, we are calculating the feature 2 depending on the feature 1 and the causal structure. So for this network, this feature 2 is only dependent on the feature 1. So we are calculating feature 2 based on the number values of feature 1. And this mapping from feature 1 and feature 2 is also be sampled from some sets of the function. So for example, the candidate of f is some linear function, or some Lelu-like function, or step function, or many other different functions. So, and if we make this whole data set for the tables, we will train the TAP-PFN with this many tables, and for illustrate how illustrate the aim of training the TAP-PFN, let's think of a more simple example. So let's see the case when we are training the model predicting one output from one feature. So we are predicting just x from y, predicting y from x. Then the synthetic data will be formed like this. We have x first, and this y variable will be calculated from the f, which can be sampled from the pool of some functions of the f, like and this f can be sampled from the some distribution of the f, something like it can be like linear with probability 1f. It can be Lelu with probability 1f, something like this. And we are also sampling the train set and test set. So it is also like it can be sampled from the probability distribution. And because we have a train set and test set, so what we want to do is we are making a function, this PFN, which minimizes its output, the difference between its output and this y test value. And because this FNT is sample from the probability distribution, we are calculate the expectation over the probability distribution of like, this function and the train test splitting. And because this, although this, I illustrated some simple example, but it could be more like complex, then we can just sample from that complex probability distribution and calculate the expectation with this many synthetic data.
Sorry, what is P? I don't know.
P is probability of probability distribution of F. So F is some function mapping x and y.
Sorry, what is T?
T is like probability distribution for splitting the training and test. So it is something like this some portion of training set can be the probability distribution. So if we generalize this to the like more features, like 10 or more features, then we have we also have this probability distribution for the F function, but it is more complex and more difficult because it contains more like causal structures. And with this feature there can be many features, like 20 features or 50 features. Like this, and these features, this number of features can be also sampled from the some distribution, like uniform or. Then we are just doing the same thing. We are generating many data set, and we are calculating this loss over the whole distribution of this F. This big number of features and the splitting of the training and testing set.
So for the causality, we also have the list of causalities.
Causalities. You mean so? Yes. You mean this function?
I mean the 1, 2, 3 arrows.
Arrows.
We have the predefined list.
Yes. There is some. It contains many functions.
Are you conditioning on fixed outcome variables, or is that something else that you treated? Like they're just gonna have one outcome variable in the last column?
Outcome variables.
Because there's a lot that's bottled up into the graph. You've got a directed acyclic graph, and all the possible TAGs, right? But then you also have different choices of outcome variable.
Yes. Yes. Right. So for this slide, I just illustrated just for one output, but it can be generalized to the multiple outputs. So there's more like more generalized and advanced like procedure for the training, but I put it as an like appendix so that you can check that slide, or you can directly check the papers, a paper. So using this training objective, they first generated 130 million synthetic data sets, and they pre-trained their TAP-PFN model, and they compared this TAP-PFN model with other prediction models such as linear regression or neural network or CatBoost. And they first checked the performance of this TAP-PFN with simple example. So we are assuming the true function of the data is y equal absolute x, and we are sampling some data point from that from this set, and we are checking if these models predict the other points well or not. So first of all, this the first law is the true function, and this blue curve is the prediction from the TAP-PFN. As you can see, this TAP-PFN performs well. It reconstruct all the true functions. But if you use linear regression, of course it is really bad. And if you use neural network, then it is bad for this oscillatory behavior. This neural network does not capture this oscillatory behavior. And if you use CatBoost, then as you can see, it reconstructs the most of macroscopic pattern of the true function. But as you can see there, because it is like tree model, it basically shows this kind of discontinuity. So based on this figure, we can say that TAP-PFN has the most, like, how to say, has the best performance for the predicting the toy example.
Sorry, Martin. The TAP-PFN function that you're plotting there, is this like the posterior over all the different functions that you consider? It's a little bit smooth over there, so it's not like you're picking a most likely function.
Yes.
But the tabular data, the sample ID usually not sorted according to the time or, so tabular data may not have temporal structure. So in that case, can we use this approach?
I think if we consider the time as another feature.
So time column should be included to use this one.
I think so.
For time, the x-axis can be anything.
Can be anything. Then, but in this case, they have some smooth.
Could be height, weight, it could be, could be anything. But yeah, if you want a function of time, then you just make time a feature, right?
Oh yes, right. So they applied this TAP-PFN for the real-world datasets. They used 29 classification datasets and 28 regression datasets, and they applied prediction models, and they compared the evaluation metrics such as AUC, ROCs, and accuracies for classification datasets and RMSE and normalized R2 for the regression dataset. So, and this is the result. So if you see this figure, the rightmost bar is the TAP-PFN. As you can see, this TAP-PFN has the highest AUC, ROC, and accuracies. So TAP-PFN has superior performance in classification datasets. And also for the regression datasets, the rightmost bar is TAP-PFN, and this figure shows that TAP-PFN has a superior regression performance. And Because CatBoost is right now the most popular algorithm for prediction. They particularly compare the performance from the CatBoost and the CatPFN. And this y-axis is the evaluation metric for the CatBoost, and this x-axis is the evaluation metric for the TAP-PFN. And this each point represents each data set. So if the point is in the under area, then it means that TAP-PFN perform better. And as you can see, most of the points are in this under area. It means that for the most of the data sets, this TAP-PFN has a better performance than the CatBoost model. And this TAP-PFN is even more efficient. The efficient means that this x-axis is the time for hyperparameter optimization, and if we spend more time for the hyperparameter optimization, then the evaluation metric will go up. But if you see this graph, even we spend just 5 seconds for the hyperparameter optimization, it is better than the CatBoost model, which spent really many hours to train to optimizing the CatBoost model. And it was same for the regression problem. And they also checked if this TAP-PFN is robust to some manipulation for the data. So first of all, they permuted one of the feature in the data set, and they add this permuted feature as an unimportant or useless feature. Then, if you see this graph, this light bar, the light color bar is the data set with many useless features. Then, if you see the CatBoost, if there is many useless features, the performance become bad. But for the TAP-PFN, it maintains some reasonable performance. And we also added some outlier by selecting some values in the table and just multiplying that variable, like 50 times or something like that. And as the outliers become more and more, if you see the neural network were linear, it performance drop highly, drastically, and both TAP-PFN and CatBoost is robust to this outlier, but if we compare this TAP-PFN and CatBoost, then TAP-PFN has a higher performance than the CatBoost.
But what does it mean by outlier fraction is 100? Outlier. I mean, there are hundreds of outliers.
I think so. That's what I understand. So this whole result show that this TAP-PFN is superior over the other prediction models. And at last, so I think we can make a more specialized TAP-PFN by changing the structure of the synthetic data set. So for example, if we want to make a TAP-PFN specialized for the oscillatory data set, then rather than give like uniform, just random features for the beginning node of the synthetic data, we can give like cosine function or other oscillatory data set for the beginning nodes, so that all the synthetic tables have some kind of like oscillatory behavior, so that we can make a specialized oscillatory specialized like model for TAP-PFN. So at last, so to summarize, this TAP-PFN model is the model which predicts which make a prediction based on the whole training set and the feature of the testing set, and it has so that it can be applied for any real-world data set with a table form, and it has a superior performance over other prediction models in the world now. So that's it.
Thank you for your talk. So how much data would we need for TAP-PFN to perform well? For example, I am dealing with a time series data. How much data should I feed to TAP-PFN?
So in paper they said it can be applied up to the 50,000 samples, and 500 features. So if a table is smaller than that one, then it can be applicable. But you mean
I mean like the smallest allowable
smallest
data.
allowable data? Mm. Mm. Actually, they did not mention, but I think actually it because it has to like see the context of the data, so that they at least they should have minimal data set for reading that context of the data, but the minimal requirement for a sample will be smaller than the other prediction models because it is pre-trained, and if we with this minimal data set, they can find a similar data set which is in the like synthetic data set or pool of synthetic data set. So maybe it can be the minimum requirement of the data set will be smaller than the other prediction models.
So if we don't have any causal relationship list, can we use this algorithm to
So so you mean you have a data set, but you're not sure if this have a
yeah, we don't know
causal
about the
relationship.
relation, yeah.
So
They anyway sample the causal relationship from the candidates, so we can make, yeah.
so if their like true structure of the data set is doesn't have a causal structure, then it is like straightforward, and it is makes sense that we cannot make a prediction. But if there is at least one causal structure, then this causal structure will be like highly with high probability this causal structure will be sampled in a synthetic data set. Then I think it can make a prediction.
Suppose you mask out one of the columns. So you always you have a causal model to generate the features and the outcome, right? But one of the problems with regression is something unobserved that confounds the causal structure. So I mean, it seems like you should be able to test that just by taking your synthetic data and masking out one of the columns, just eliminating a column, and seeing if the result still holds.
Mm-hmm.
I do have a question regarding like the training data set. So if I understand well, you give one table, one table is one data set, and you give multiple tables so you can train the model, right? But suppose, for example, you have a time series for different time series for different patient. So you have like one table per patient. But you don't measure always the same, well, you don't measure the same variable always for the same period. Like for example, for one patient, you measure something for 10 days, for another it will be for 5 days, and for another it will be for 8 days. Does this will impact the performance of the algorithm, or even sometimes prevent the method to find a model?
So you mean like we have data for like 100 patients, and the data size for the 100 patients is different.
Yeah,
And
so
how can
basically what happens if we have a different number of rows or even also different numbers of columns? Like for example, we are at the beginning we start with a certain set of features, but then we decide to add more features, or some are judged useless, so we remove them. So what happens if we don't have the same numbers of observations and the same number of features? Does this impact the model or not?
So in that case, I think we can make we can integrate all data from the patients. So if they have for example, if my data have like BMI feature, but your data doesn't have BMI feature, then we can just first integrate the table, and your BMI feature as like just missing data. Then I did not talk detail for the missing data in this slide, but they also take account for the missing data. So I think they can at least perform the prediction. They can make a prediction using that. But for I'm not sure if how much that will impact the accuracy of the prediction.
Okay, thank you.
So in the slide, represent the fitting. You showed some fitting graph. Right?
Oh.
Yeah, in this graph, if you see the step function column, somehow tap FPF and try to keep some smoothness or continuous. Do you know the reason why? Compared to the cat boost show the better performance of the step function.
Maybe we are this I think this outcome this curve will be highly impacted by the predefined list for the causal functions. I mean the linear or level or something like that. And if there is most of the functions there is the continuous function, then maybe this TAPPF also want to make a continuous prediction. But I'm not sure. But in my opinion, if we put only this continuous function for that function list, it may show step function like calculus. But I'm not sure.
Okay.
It's just my hypothesis.
Thank you.
Did they mention any more structure of TAPPF is which model?
Model. It is actually based on the neural net.
you can plug in any size of data.
So it is based on transformer, which is usually used in language.
It seems like they argue that their method is perfect. I wonder whether there are some weaknesses.
Weakness. Maybe so there weakness will be one thing is it takes a long time to be pre-trained. I mean, we have to pre-train the TAPPF, and they said it took 2 weeks for pre-training and with like 8 GPUs.
So the time that they put in the abstract did not include the pre-training.
Oh yes, because it makes sense because if we once pre-train that TAPPF, then we don't have to train more. We can just plug in the data.
Like an LLM model.
So for us, we can just use their model, their pre-trained model, pre-trained model.
So
Okay.
that means with this model, we don't need to do the hyperparameter tuning or train test separation and something like that.
But what if our data is not included in that pre-trained model?
Because
Then there should be some domain mismatch, right?
So I was worried about the test. So anyway, it trained the model with various samples, but if our data is outside of the
Yeah,
training
distribution.
then I think always the learning model is very bad for extrapolation.
Yeah.
So performance. But he maybe the later part he mentioned that you can specialize this model.
Yeah.
We can modify that. What's it, the domain, the training, static data domain, something like that. So
Yeah. Or near future, they might provide some fine-tuning method. Yeah.
and did they mention anything about missing data inside the tabular?
missing data.
So although they of course they mentioned that if the data some data is permuted, so it doesn't give any information, it automatically ignores it. Maybe this model could be very robust to missing.
I think so, and I think they propagated it. Not a missing data, but they just removed some features or samples. So this figure is for permitting the feature, and this is our layer, and this is drafting samples. And instead we are removing some data, and this is the drafting the features. We are removing some like features. And we also have this missing values. So, if we see this two graph, I think it is robust to see.
But it doesn't work when you drop features. Nothing does. That's what I was asking before.
What do you do? Drop doesn't work.
So,
Well, I asked him what happens when you drop features.
Drop features.
Look, accuracy goes down a lot.
Yeah, but it's still the best.
Maybe that means that the feature that they drop features.
This is the major problem in regression. You don't know if you've observed everything you need to know. You have unobserved confounds that correlate variables and cause all kinds of problems.
Do they say, well, which dataset can be applied to this method? Because we were talking about domain earlier, but something I'm thinking well, you mentioned that they trained this method onto 29 or 28 datasets, right? What was the features they used?
So for it is pre-trained on many synthetic dataset, and it is they plug in the like 29 real-world datasets for this TPM model. And your question is which specific feature were used in that 29 dataset?
My question would be more like, okay, I have my table which contain single cell data, so I have like each rows would be a cell and each columns would be a gene. If I plug, if I give that to TabFM, can I get some predictions? Like, can I get, for example, the cell type depending on the gene values?
You need that label. So
Yeah.
X train, Y train. You need, so for example, for each cell.
Yeah, well, X train would be, well, each columns in X train would be one gene, and the Y train would be the cell type.
Right. In that case, they can.
Can you go to your loss function?
Those
Such that minimize. F is very specific function, but if you minimize the loss so that the PF and theta is close to F. I mean, I don't understand this. F is such a specific function. So you only want to find such function.
You're averaging over F's.
Average
You've
of
got an
F.
expectation over F and T.
Yeah. So that makes some sort of universal approximation.
Yeah, it's perfect.
Perfect like you.
Oh yeah. So I tried to check the codes, and according to that, they separately train the model. for regressor and classifier. Yeah, so maybe, yeah, it's quite natural that things separately for the regression from classification part.
아니, 화면을 잘 되거든요.
Here the PF and zeta is just the learning structure.
Yes.
Did they provide any proof, or is this black box?
Proof. That there is no proof.
machine learning paper.
Is it a black box model, like neural networks, or?
Yeah. So the PFN is based on the neural net.
I still wonder why minimizing the average. Do you have any intuition? Minimizing the average.
So your question is
Why
this?
minimizing that noise that gives us the desired
if we want to make PFN perfect, then this PFN zeta, this value have to be this y test value.
Yeah.
And this y test in the synthetic data set is fx test. So instead of this fx test, this is, you can just think this as a y test in the test data set.
Yeah, even if we write down as a just D train, inside of that, the F is actually contained in D train.
Oh, yes.
Y itself is generated from F. So it's like, so it's that the average means that we are considering the various types of functions. I think that's the.
Yeah, you're averaging over different functions and different, D train is T.
Yes. So this is the function of this f, and the the splitting of trains is just t. So all this value is determined by f and the t.
So if one function isn't very good, if it's wrong, then P is small and it doesn't contribute the error might be very large, but it doesn't contribute very much to the expectation. So sort of adjusts for that.
So for the training, they didn't aim for Y value. They didn't put any noise when they did the synthetic.
Noise.
Yeah.
I don't see any description for any noise in their presentation.
They have to. You mean Y is deterministically a function of all the x's? It's not a regression unless you have some noise in functional relationships. Like in a standard regression, you always include some noise in the outcome variable.
Maybe, maybe in that case. It's easy to make some overfit transition. Because there's no, they didn't cluster any of those.
It does sound too good to be true. Even if they just wanted to do linear regression, it seems like a tough task. Just to average over all the possible DAGs.